Alright, welcome back guys for part 2. So we were looking at basically doing some arithmetic with functions. Adding, subtracting them, multiplying them. We even saw an example in which we divided them. And we also saw some examples in which we weren't working with just the functions, but we were actually substituting a value for x. So anyway, now what we want to do is look at, so let's say we add two functions together and we get this new function. Okay, now if you remember that lemonade stand example, if we have a revenue function, a function that models or predicts the revenue, and we subtract from that function the cost function, then we get a new function, and it's the profit function. And it's a function of the number of cups of lemonade that we sell. Okay, so then the question becomes, so this new function that we get, what is its domain going to be? Now in that lemonade example, the domain would be the same. It's just positive integer values or counting numbers, right? Because you can either sell 0 cups of lemonade or 1, 2, 3, 4, 5, basically counting numbers. Okay, that would never change. But occasionally you can end up with a new function in which the domain has a restriction in it, and that's what we're going to look at today. And I'm going to try to keep this as simple as I can without going into too much conceptualization, but it says to find the domain of the sum, the difference, the product, or the quotient of two functions, f and g. Okay, so what you're supposed to do is find the domain of the two functions individually, and then the functions, the sum, the difference, and the product will have the same domain, and it'll be the intersection of the domains of those two original functions. Okay, so in other words, the set of all values that are common to the domain of both f and g. Now, when f and g are both polynomials, and that's what they'll be most of the time, when they're both polynomials, whether they're linear, quadratic, cubic, if they're both polynomials, then the domain of both the sum, the difference, and the product will be all real numbers, okay, because that resultant function will also be a polynomial. The only time you have to be careful is whenever you see an instance like this guy right here. Basically when you have an x in a denominator in one of your functions, or if you're finding the quotient of two functions, then one of these functions is going to become the denominator, and you'll have an x in the denominator again. That's really the thing you're looking out for. Okay. Alright, so let's look at example 4. And guys, to my knowledge, I think my examples pretty much mirror the problems from your homework that address the domain. Okay, so just kind of use these as examples. It says for the pair of functions f and g, determine the domain of the sum, the difference, and the product of the two functions. Now notice it doesn't ask us to actually find the sum or the difference or the product. If it did, then we would literally either add the two functions together, subtract, or multiply the two functions the way we did in part 1. Okay. And they're just asking us to find the domain if we were to add, subtract, or multiply these two functions together. We'll look at these two functions. F is a quadratic polynomial, and g is a linear polynomial. Okay, so these are both polynomial functions. Now I'm going to put this in the notes. Both are polynomials. Okay, and because of that, since they're both polynomials, if we add them, subtract them, or multiply them, the resultant function will also be a polynomial. And so therefore, the domain of the sum, the difference, or the actually, let me just put the word and. Product of these two functions will be all real numbers. Okay, let's see. I guess I'll write it in set builder notation. All values of x such that x is a real number. Okay, and again, it's just because these two functions are both polynomials. Okay. Now, if it had asked you what would the domain of f divided by g be, that wouldn't be all real numbers. And the reason is because g would end up being in the denominator, and because of that there would be a restriction. There would be a restricted value of x. Okay? We will see actually one like that here in just a second. All right, let's go to example 5 here. So for example 5 it says, for this pair of functions, f and g, determine the domain of the sum, difference, and product. Okay. Well, g is a polynomial. It's a cubic polynomial, but f is not. F is a rational function. Okay. So the domain for g would be all real numbers, but that's not going to be the domain of f. In fact, because f has an x in the denominator, the domain of f is basically going to be all values of x except for 7. Because looking at this denominator right here, guys, I can see that when x is 7, the denominator would become 0. And that makes the function undefined. So you could say, well, what value of x would make that denominator 0? Well, if you add 7 to both sides, you're going to get x is equal to 7. Okay, so in other words, the domain is all real numbers except for 7. So x cannot be equal to 7. Now, the domain for g is all real numbers. Now, the intersection of those two sets is going to be all real numbers except for 7. Or in other words, if you're trying to find the domain of the sum, difference, and product, and one of your functions is a rational function like this, then the domain for the sum, difference, or product will just be whatever the domain for this rational function is. Okay? Or in other words, if 7 will not work for this function, then it's not going to work for the sum, difference, or product, okay, of these two functions. All right, so let's write this. The domain for the sum, difference, and product will be, again, I'm going to write this one in set builder notation. All values of x such that x is a real number and x cannot be equal to 7. Okay. So when one of your two functions is rational, you're going to have a restriction. You know, if we were to add these two functions together or subtract them or multiply them together, we would get a new function, and this would be the domain of that new function. That's what this question is basically asking us. That new function could take any real number except for 7. 7 would make it undefined. All right, so let's look at one more. Example 6 here. So, example 6, it says, for this pair of functions, f and g, determine the domain of f divided by g. Okay, so f and g are both actually polynomials. They're both linear. linear functions or linear polynomials. So the domain for f and g is all real numbers. However, we're trying to find the domain of the quotient of these two functions. So what I would do, guys, to begin with is just actually construct that quotient real quick. Okay, this just would be f of x divided by g of x. Okay, so you're just going to write it out. F of x is 5x minus 7 over g of x, which is 7x minus 21. Okay, so this would be the resultant function right here. So now, just looking at this, we can tell the domain's not going to be all real numbers because there's an x in the denominator. And so consequently, we will have a restriction on the domain. And to find that restriction, we're just going to see what makes this denominator 0. So in other words, you take that denominator, you set it equal to 0, and if you solve it for x, it will reveal the restriction. So the first thing we would do is add 21 to both sides of the equation, and that would leave us with 7x is equal to 21, and then we would divide both sides by 7 to isolate x, and we get x is equal to 3. 21 divided by 7 is 3. And so 3 is the value that's restricted from the domain of the quotient of those two functions. Okay, in other words, x cannot be equal to 3. Okay, for the quotient of those two functions. So we'll say the domain of f divided by g is all values of x such that x is a real number and x cannot be equal to 3. Okay, so any other value or any other real number for x would work. It would always give you an output or a y, but 3, the number 3, would not. Alright, so those are 3 examples, guys, of finding the domain of that resultant function, whether it's a sum, difference, product, or a quotient. Okay, like that last example. Alright, so that will pretty much conclude section 2.4. And now we're going to move into chapter 3, and we'll do 3 sections in chapter 3. Okay, we're going to be working on solving systems of equations. Alright, so I'll see you, I believe we go to 3.5 next.